Alrighty, folks, welcome back. It's me, Mr. Hess, ready to teach you another lesson out of Chapter 9. We are now up to Section 3 of Chapter 9. And again, remember, Chapter 9 is focused entirely on circles. And in this section, we're going to talk about arcs and chords of a circle and some relationships that they might have with each other within a circle. All right, so we've got three theorems. As you can see, I've already drawn some pictures up here, and we'll go ahead and jump into our first theorem of Chapter 9, so Theorem 9-1. If you look on your list of postulates and theorems, you'll see that this theorem simply states that if we have a single circle or two congruent circles, all these theorems are going to start like that with either a circle or two congruent circles. But if within a circle here we have two chords, remember a chord is any segment that runs from edge to edge of the circle. Okay, but if we have two chords that we know are already congruent, then not only will the chords be congruent, but do you see how they also intercept an arc right here? So this arc from there to there is going to then also be congruent to this arc from here to here. Okay, so this theorem says if chords match, then their arcs do as well, basically. All right, so that one's easy enough. Theorem 9-2. Theorem 9-2 is probably the theorem that we're going to use quite a bit in this section, at least, of the textbook. But in Theorem 9-2, again, notice we have a chord that I've drawn on our picture here of a circle. Again, a chord goes from edge to edge of the circle. And then, according to Theorem 9-2, though, they say if you then were to draw a diameter that's perpendicular to that chord, so if we do something like this, if we draw a full diameter going through the center of the circle, and if we draw it so that it's perpendicular to the chord, then it's going to bisect the chord and the chord's arc as well. So see that chord right there? If you run through the center of the circle perpendicular to the chord, it cuts it in half. It bisects it. So those two halves of the chord will match, and the arc down here also got bisected as well. So those two halves of that arc would be congruent. In fact, technically, the other parts of the semicircle, see how the diameter cuts it into a semicircle? So not only would these two match, but these upper halves up here would match as well, those arcs. Now, when we use Theorem 9-2, though, we're going to be using, you might say, a slight variation of it. Instead of having a full diameter, we might shorten that up, and it doesn't even have to be a radius in that, for that matter. Like what we're going to do is this. Most of the problems that will utilize Theorem 9-2, again, would have a chord, but and let's say there's the center of the circle, but instead of drawing a full diameter, we might just draw a segment that is perpendicular, like they did here, perpendicular and going to the center of the circle. So we're only using this part of the diameter. It's like we're ignoring that part, we're ignoring that part, see? We're just going to use that little part there. As long as it goes through the center of the circle and is perpendicular, it's still going to bisect the chord. Okay, but then here's the other difference that we're going to do on ours. On our variation down here, I'm also going to run a segment from the center out to the edge of the circle there. So as you can see, even though I didn't make that very straight, as you can see, that caps off a right triangle then. So it makes it into a right triangle. So on a problem like this, by the way, we're going to refer to the different parts then in this picture. Like, for example, from the center out to the edge, you already know that that's called a radius. Okay, so there's the radius. The chord, the original chord, is this entire distance from there to there. So that's the chord. because we're going to do some word problems that involve these, so you'll want to know this terminology. Radius there's the chord. Now remember, the chord, though, is twice as long as the side of this right triangle, though. And then finally, this last side right here of the right triangle, we could refer to that as the distance that this chord is away from the center of the circle. After all, we always measure distance at a right angle. So if we're always measuring distance at a right angle, you could say that this chord would be that far away from the center of the circle since it's at a right angle. So again, this is the distance. I'm trying to write distance there, sorry. Let me try that again. Distance from the center. It's how far the chord is from the center. The chord's distance from the center. All right, so that'll come in handy when we do our word problems that involves a chord and how far it is from the center and a radius. All right, so let's look at our last theorem over here, Theorem 9.3. This last theorem states that in a circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. Okay, we just talked about that distance from the center here. Okay, and if we want to look at that idea again in depth here, you know, like say we've got a circle here that has that center point. The longest possible chord we can make, remember, is a diameter. And it goes right through the center of the circle, so its distance from the center is 0. And that's the longest one we can make. But then I hope you understand that as I work my way further and further and further away from the center, the chords get shorter and shorter. So there's a direct correlation between the length of a chord and its distance from the center. So if you realize that, then this theorem is simply stating then that if two chords are exactly the same distance from the center, remember that distance is measured at a right angle. So if I ran a segment from here at a right angle, and if I ran a segment from the center to there at a right angle, and if these distances are the same, so if that distance and that distance match, then as a result, the full lengths of the chords have to match as well. So in this picture, AB, that full chord, would match this full chord, CD. But only if they are the same distance from the center. Okay, and it makes sense when you think about it in terms like that, where a diameter is the longest, and the further away you get from the center, the shorter the chord gets. All right, so there's our 3 theorems for this section. I do have just a little bit more notes for you here. I just want to mention that, you know, if you have a circle, and if we draw chord after chord after chord that are all attached to each other, so like this, you know, maybe a chord there, and then at the end of that one, start another chord, maybe at the end of that one, you know, draw another chord, and at the end of that one, maybe draw another chord that meets up finally with that one. Okay, if you do this, you know, I don't care how many chords you make, do you see that it makes a polygon that is fit perfectly inside of the circle so that each of its vertices are actually on the circle itself? Okay, there's a term for that then. This polygon in here then is called an inscribed polygon. Okay, to inscribe something means to fit it inside. Inscribe inside. Okay, so, but of course, the reason I'm bringing that up in this section, we've been talking about chords in this section, and every side then of an inscribed polygon is in fact then made up of chords. All right, now let's keep all these ideas in mind as we try some problems now. I'm going to leave this up here because when we get to these problems that involve that idea, this will be a good reference to look at. Okay, but here's our first practice problem. Let's say that I have a circle and I've got chord, chord, chord. They're all marked congruent. And let's say that this arc from here to here is 120 degrees. And I want you then to find the measure of this arc down here, let's say. We'll call it X. Okay, so be careful on this one. The way I've drawn this can be deceiving. I did not draw it to scale, you might say. You know, it's not a very accurate drawing. So if you go off of the information I've given you on this one, you're going to find that this is not 120 degrees matching that. They're not a match. You know, some of you might think, oh yeah, they are. Because if I were to close this off, it looks like it's going to make a square. Okay, be careful. You're making an assumption here. If I were to close that off, that chord's going to be the same. Do not assume that. Okay? Like I said, I didn't draw it very accurately to begin with. Because if you do some math here, if this is 120, you know that all the arcs around a complete circle should add up to 360, right? So if I take the 120 that I already have here off of 360, you can see that's going to leave you with 240 degrees. All right, now, I do know from my lessons in this section that if all three of these chords match, then all three of these arcs match. So I know that the rest of the circle is made up of three matching arcs that should add up to 240. So you probably guessed it. At this point, all you got to do now is take 240 and split it equally three ways. And you'll notice it does not come out to 120. 3 goes into that 80 times. So that's 80 degrees for each of these. So this is 80 degrees, this is 80 degrees, and of course, more importantly, there's my answer. X is 80 degrees. Okay, so that's problem number 1 that I wanted to try with you. Okay, let's try another. This one I'm going to call problem number 2 then. And in this problem, we've got our circle here. There's the center of the circle right there. And let's say that we've got a chord there and another chord here. Let's say that I draw a segment from the center at a right angle to that chord, and its distance matches another one that I made from the center of the circle to this chord. Okay, so if I told you then that the entire length of this chord is 24, and if I told you then that this is point A, this is point B, and this is point C, if I wanted you to find just this BC right here, BC equals what? All right, now we're going to use a couple of theorems for this one. First of all, we had a theorem that I just mentioned earlier that if two chords are both the same distance from the center, and distance is always measured at a right angle, just like we had here, distance from the center is at a right angle, then if those distances match, then so do the full lengths of the chords. So based on that idea alone, if this full one's 24, I know from A to C is also 24. But I wanted from B to C. Okay, so now I'm going to use a different theorem that I just had in this section that stated that any segment coming from the center of the circle at a right angle to a chord will then split that chord into two equal halves. So these two halves are going to be the same. So if the whole thing's 24, then BC, as you can see here, is only half of the 24. It's only 12. Okay, so that's got to be 12, that's got to be 12. Same up here. These two halves have to match because, again, the segment from the center of the circle at a right angle bisects it. So these are 12 and 12. So it's kind of like a mirror image, you know, they match. Okay, That was problem number 2. Let's try problem number 3. Okay, in this one, I've got a chord. There's the center of the circle. And let's say that from here at a right angle down to the chord, that length there is 12. Let's say that this distance is 20 from the center of the circle out to the edge of the circle. And on this one, let's say that I wanted to find, if I call this AB, this full length of the this chord, I want to find AB then. AB is how long? All right, now, this is one of those problems, if you look down here at my notes that I had down here, it looks very similar, see? We've got a scenario where you got a full chord. We've got this little segment representing the distance from the center at a right angle to the chord. And, of course, this last part that caps off the right triangle, that part that's 20 there, is the same as the radius of the circle. It goes from the center to the edge of the circle. Okay, so on a problem like this, since it forms a right triangle in here, we're going to utilize the Pythagorean theorem, the most famous theorem of all. Okay, and of course we know the Pythagorean theorem is a squared plus b squared equals c squared. Okay, on my little right triangle here, it's important that you be able to recognize then the hypotenuse, because that's got to go in for the c, and the hypotenuse is always across from the right angle. So in a scenario like this, the radius is always our hypotenuse. So 20 is going to go in for C. Okay, that means 12 is one of the two legs. And our other leg is really just this part right here. From, the middle of the chord out. It's not the full length of the chord, so be careful. X is not going to be our final answer, but it is going to be exactly half. Because, see, that splits that chord, when you drop that distance, that splits that chord into 2 equal halves. Okay, so 12 and X are going to be both the legs. Okay, we're going to do Pythagorean theorem. X squared plus, that'd be 144, and then this would be 400. You want to get the X by itself, so we would subtract the 144 over to the other side. That gives us X squared equals 256. Okay, and that's convenient because to get rid of the square, you got to do a square root. And the square root of 256 does come out to a nice whole number. It's 16. Okay, so now, be careful, again, that's not your final answer. That's just for this side right here. That part's 16. That means this over here is a matching 16. And then AB, the full length, of course, would be not 16, but 16 times 2, or 32. So there's our answer. AB is 32. Okay, I'd hate for you to put 16, you did all the hard work, and then get it wrong. So be careful. On problems like these, always double check and make sure you found what you're supposed to find. Okay, these tend to be the hardest ones, as you can see. A little bit more work than those other two problems we did earlier. Okay, so we're going to keep doing more of these. Only now, instead of giving you the picture like that, I want to try a word problem version of these. Okay, so give me a minute here. I've got to write out the word problem here. But so for this fourth problem, suppose a chord is 20 inches. 20 inches long and is 24 inches from the center of the circle. From the center of the circle. Find the length of the radius. Find the length of the radius. All right, so like my notes here down here, I'm going to make my own little circle. Okay, I'm going to draw a chord in it. They said the chord is 20 inches long. So this entire length along there is going to be 20. And then they say it's 24 inches from the center. Distance from the center is measured at a right angle. So if this is the center of my circle, distance is then measured at a right angle from that center, or from the chord to the center, and that's 24 inches. They want us to find the length of the radius. The radius is always what caps off the right triangle there. So we're trying to find R in this case, that radius. Okay, so like we just did earlier, I want you to notice it makes a right triangle, which means we're going to get to utilize the Pythagorean theorem. Okay, I'll do that over here on this side. A squared plus b squared equals c squared. Remember, the hypotenuse is c, and it's always across from the right angle, so it's the radius here. So that's what we're trying to find, the R. Okay, my legs. My legs for my right triangle are 24, but be careful down here. That's not 20. Instead of 20, do you see that this gets split in half, 2 equal halves? So instead of 20, this would be only 10. So when you go to plug into the Pythagorean theorem, put in 24 and 10 for your legs this time. All right, 24 squared is, I'm going to say 496. 24 times 24, oh no, 576, sorry. 10 squared is 100. R squared is R squared. Okay, now in this case, I've already got the R by itself, so in this case, I'm going to add these to get 676. Which, by the way, again, conveniently is a nice whole number when you do the square root, because that's what we're going to do next, is the square root just to get R by itself. Okay, and the square root of 676, you're going to find comes out to 26. Okay, and in the end, remember, we were trying to find the length of the radius, and that's what we did right here. So that is our final answer on this one. 26 inches, you might say, is the length of the radius. Okay? Let's try yet another of those in a word problem format. And the word problem format isn't bad at all as long as you keep this handy. This is a great reference to have handy, so when you do these problems, you can just kind of match up when they label each of the parts: radius, distance from center, and chord, because they'll always mention each of those. Okay, so let's try one like this. Suppose the diameter of a circle is 30 centimeters long and a chord is 24 centimeters long. Find the distance between the chord and the center of the circle. Between the chord and the center of the circle. All right, so again, we're going to have something similar to this that involves a chord. Okay, and normally we just use a radius. They mention a diameter in this one. They say, suppose the diameter of a circle is 30. Okay, now I'm still going to conveniently locate my diameter at the end of the chord. So my diameter is going to run all the way to there instead of just stopping at a radius. And that diameter was 30. So if this entire length of that diameter is 30, then of course my radius from here to here should be exactly 15, right? 15 plus 15 would be 30. Okay, I only want the radius because that's what's going to make our little right triangle in this problem. Okay, now they mentioned the chord is 24 centimeters long. So this entire length along the bottom here of the chord is 24. And we want to find the distance between the chord and the center of the circle. So we want to find the distance that chord is from the center, is what they're saying. We want to find that length right there. That's going to be our x, our unknown. But as soon as I drop that from the center at a right angle, remember it splits this into 2 equal parts. So instead of 24, each of those is only half of that, 12. So when I go to work with this little right triangle here, okay, instead of using the full 30 for the diameter, we're going to use 15 for the radius. Instead of using the full 24 for the chord, we're only going to use half of that, 12. So off to the side over here, I'm going to go ahead and do that Pythagorean theorem. A squared plus b squared equals c squared. Across from the right angle, that radius there, remember, will be our hypotenuse. So 15 goes in for C. The legs are x and 12, as you can see. All right, here we go. 12 squared is 144. 15 squared is 225. I want to get x by itself, so this one I'll have to subtract the 144 over to the other side. So I'm left with x squared equals, let's see, 81. Well, that's convenient. When we go to do the square root of 81, of course, you get a nice whole number of 9. So there's our x. That's our distance from the chord to the center of the circle. So that's our final answer on this one as well. Okay? So be careful on these types of problems. The chord always gets cut in half. And if they happen to give you a diameter, you'll have to cut that in half as well, because we only need a radius. Okay? All right, I've got one more problem. It's not a word problem like those were. But I got one more of those I want you to try here. In case you run into one that looks like this and you're wondering, well, how do I do that one? I forget what number I'm up to here, but anyways, on this problem, let's say here's a chord. There's the center of the circle. We'll call E the center of the circle. There's a radius by chance there, AE. And let's call this B. Let's call that D. And then let's say that there's another radius EC here that runs perpendicular, and it hits right there at the point F. So on a problem like this, they might say, all right, if AE equals 6.4 and FC equals 3, then they're going to ask you to find BD. All right, so AE, they gave that as 6.4. FC, that's this little part right here, is 3 from there to there. And they want us to find BD. BD being that full length of the chord. Okay, so they're having us find the chord. So at first glance, when you look at this up here, you might not recognize that's one of these problems, but it is. Okay, so here's what I want you to realize. Remember that the radius was used here to cap off that little right triangle. And this AE is a radius. So if you were to visualize this, imagine if I take AE and I swing it now to there, to EB. You see AE and BE are both radii, so they should match. So this is still going to be 6.4, and notice that when I swing it to there, it then finally caps off the little right triangle, just like we had down here. There's our little right triangle in that one. Okay, and then remember, anytime a segment from the center of the circle intercepts an arc, intercepts a chord at a right angle, it then bisects it. It cuts it into 2 equal halves. So those are going to match there. And on this problem, believe it or not, we can find EF. Because if you pay attention again to how AE was a radius, CE is also a radius. See it? AE, BE, CE, they're all radii. So they should all be 6.4. And if this part's 3, then wouldn't this have to be 3.4? So that 3 plus 3.4 would be 6.4. Okay, and now finally, I'm going to find this distance, x, here in our little pink right triangle. It's going to help me then find my final answer, BD, which will be the full chord. Okay, so I've got enough information now. I can finally utilize the Pythagorean theorem. So I'm going to do a squared plus b squared equals c squared. The c is the hypotenuse across from the right angle, or in other words, the radius right there of 6.4. These two are my legs of the right triangle, x and 3.4. Okay, this one deals with a bunch of decimals here, so I'm going to need to use my calculator on this. 3.4 squared is 11.56. 6.4 squared is 40.96. I'm going to get my x by itself, so I'm going to move this over here by subtracting it over. So 40.96 minus the 11.56 leaves me with 29.4. And then, of course, I get rid of a square by doing the square root. So the square root of 29.4 approximates to, you're going to have to round this because it's a big long decimal there, 5.4 approximately. Oh, now I was getting ready to circle that. That's not my final answer. Okay, so even I am human and I make mistakes here at times, but remember, in the end, they wanted us to find BD. BD is this full length. I just found X, so the full length of that chord is going to be another matching X down here, so we have to double this. We got to take that 5.4 and double it. So as you can see, my answer then is going to be 10.8 for BD. Okay? So be careful. All right, well, there you have it. That's how you do the problems in section 9.3. For homework, I gave you on pages 462 through 464, problems 6 through 12, problems 25 through 27, and problems 32 through 37. Okay, so complete that assignment. Make sure you put your name at the top and label the assignment, please. Some of you have been submitting by email your assignments without any labels. So it's very difficult for me to figure out what assignment you did. Okay, but put your name and label the assignment at the top and submit a picture of that completed assignment to get credit. Also, don't forget to show your work. Okay, so a lot of these involve Pythagorean theorem and stuff like that. So show your work, please. So I know that you didn't just jot down some answers, or else you won't get full credit. Alrighty, I will see you then next for section 4.